Really great talks for you this afternoon. Some fantastic talks tomorrow. It is my pleasure to introduce to you Praveen from Qubole, who will be talking to you about Spark. Let's give him a round of applause.
Hi everybody. So I'm Praveen Seluka. I'm a software engineer at Qubole. I've been leading our Spark effort for the last 1.5 years. So today I'm going to talk about introductory videos about Spark, and then going to talk about various challenges in running Spark on the cloud and how we have solved those challenges in Qubole. And at the end of the session, we'll also see some kind of a demo, like how we have done it in Qubole. I'll also give you some kind of access so that you can try out some Spark programs on the platform directly as I show the demos. So a quick round of introduction. So I work at a company called Qubole. It's started by Joydeep Sen Sarma and Ashish Tishu. They were the creators of Hive at Facebook, and which was later open sourced to Apache. And we offer all the big data tools like Hadoop, Hive, Presto, HBase, Spark, Pig, all these into one unified big data platform on the cloud. We make it very easy to use, and we make it highly performant. So that's what we do. A quick round of introductory slide again, like what are the highlights, like to talk about the scale at which we deal with things. We process as much as 170 petabytes of data every month. It's almost close to 200 petabytes now. And we are on cloud, so we spin up all the Spark or Hadoop clusters on Amazon itself for our customers. And we spin up on the range of 300,000 machines every month. And we have users submitting like 20,000 jobs through our API on a daily basis. And we have a bunch of customers who run clusters of size ranging from 10 nodes to 3,000 nodes. So we have some big customers who are running multiple thousand node clusters also. So that's a quick round of introduction. So today I'm going to talk about Spark to begin with, and then we'll talk about what are the cloud-specific advantages and what are the challenges and how we have solved Qubole. And I'll also show the product demo a little bit. And I'll also give you access to the product, like I'll give a free access to everybody so that they can try out all these Spark programs on the platform itself. So that you will see like how easy it is to use at the end of the day. So how many of you are familiar with Spark or use Spark already? Oh, okay. That's good. So Spark started at UC Berkeley by Mathai and his team of people. And one of the main use cases where they wanted to do Spark is like in Hadoop, it's very hard to do iterative computation. For programs like which involves machine learning or graph processing, you need to do something which is like on a multiple iterations. On a MapReduce world, it meant like you do an iteration, you dump the datasets into HDFS back, you do another iteration where you read the data back and you dump it back to HDFS and so on. So it was not a very efficient platform for doing iterative computation. So they initially wanted to build something which is like very good for this particular use case. I think that's how Spark started in UC Berkeley. And so they did a couple of things. One is, rather than going by this MapReduce paradigm, they made sure like it's a general purpose compute engine itself, like where you can give a DAG of operators. It can have iterations, like they have native support for iterations itself. And the next thing that they did is like you can actually cache the datasets in memory. For example, if you're running a machine learning algorithm like k-means, what you can do in Spark is you can actually load the complete input data in memory, which is distributed across multiple machines. Now you're running all the iterations on this dataset which is cached in memory. So you're not hitting the disk even that much. So it becomes very, very fast. I think that's one of the starting points of Spark itself. And I think later they realized the API is general enough, and it became a general purpose compute platform, and it's widely considered as a replacement of MapReduce at this point. So I have a few slides from the Apache Spark site itself, which tells like why Spark is really good. As I said, like the speed is one of the major criteria. A couple of things that led to the speed up in Spark. One is like you can cache stuff in memory, and it has native support for iterations. So algorithms like logistic regression, when you compare with a MapReduce based implementation with a Spark implementation, it was easily 100x faster. Spark is not in general 100x faster in every type of workload. It's true for certain type of iterative workloads, but not in general. The other one is like the DAG engine itself. All the tools which are running on top of MapReduce, like Cascading, Hive, they actually build a DAG of, basically DAG, which is like MapReduce jobs itself, sequence of MapReduce jobs. So you have to hit HDFS every time and you have to read back from HDFS, which was expensive. So here it's just a DAG of operators and you just stream the data across the DAG. I think the biggest reason why Spark has become very popular is because of the programming APIs. MapReduce itself is actually higher level functional programming interfaces where map is something like in Python or in Scala where you can take a collection of some set of integers, let's say. You can map to a different set of integers or you can do some transformation. So that's a map operator. A reduce is something like a function where you can do some aggregation, like how do you aggregate the data into some single number and so on. So MapReduce itself was a functional APIs in reality. So what Spark did is it took all these functional APIs which is available in Scala and Python, like map, flat map, whatever it is, like transform, for each, and made this APIs work in a distributed fashion. So you could see an example like how easy it's to write a Spark program. This is a workload program in PySpark. The equivalent MapReduce program usually has a lot of boilerplate code, and the actual code is just like a couple of lines actually. So another nice thing is why it became very popular is because like you can program Spark using multiple languages. You can use Java, Scala, Python, and R. I think Python and R has been the biggest hit amongst data scientists. And it kind of enabled all these Python R users who were doing stuff in a single machine into a distributed computation platform itself, where you can now deal with data sets which doesn't fit in a single machine. You can use PySpark to do some computation, do some transformations, and then bring the data sets back into one process and do whatever you want. Like it enabled those set of users. Another big thing about Spark is like once you have the underlying Spark engine is basically a DAG engine, so you give it a DAG, it can just compute the DAG. And the APIs are so expressive that it became very easy to write algorithms on top of these APIs. So people like started implementing like algorithms like k-means and other things. So at some point it became a library of algorithms. So you have a library of machine learning algorithms and the graph algorithm which are implemented on top of the Spark APIs. So these are available as part of the Spark project itself. So MLlib and graphics is, you can consider it as library of algorithms which is using the Spark APIs underneath. And then there are a couple of other things. One is streaming. Spark itself is a batch processing platform where you give an input data set and you transform into something else or you do some batch computation. And there was an interesting project which is streaming. What it does is it takes in the continuous stream of data, breaks it into mini batches, and does the computation on the mini batches. So they extended the Spark model, the Spark batch processing model, to do stream computation also. So this is actually a very big interest at this point. And a lot of users need some kind of a SQL interface. So there is Spark SQL right now for those type of users who want a data frame like API or a SQL type of interface to access those data sets. So these are the four major areas, verticals or areas which is built on top of Spark right now. And the good thing in Spark is you can combine all these things into one program itself. For instance, if you want to do some machine learning stuff, usually you have a series of steps. Like you have raw data sitting in some persistent store, you do some cleansing, you do some transformation, you do some feature extraction, and then you train the model, and then you do some prediction, and then you do some charting initialization. Like it's like a series of steps together. Before Spark, I think there were technologies where each does one step. So there was a cost of using multiple technologies and putting the data out into some persistent store where the other system can pick up and so on. So in this case, it all became part of one program. You can write one giant program which does everything for you. So it unified all the capabilities in a really nice way. And another thing is like Spark itself doesn't have Spark itself has a cluster manager called standalone. But otherwise, it can run on other cluster managers like Mesos or Yarn also. So if you have a Mesos or Yarn cluster already, you can submit you can submit Spark jobs as Mesos application or a Yarn application. So if you already have an environment which has these resource managers, you can just use Spark becomes yet another application in those environments. And Spark, unlike Hadoop, Hadoop has like the storage component, HDFS, Spark doesn't. Spark is just a compute engine, it doesn't have its storage component. So what Spark did is for all the storage related stuff, it continues to use the Hadoop file system API. So all your data sets that are living in HDFS, Cassandra, HBase, for which like you must have had like Hadoop programs to read and write from these sources. It internally uses the file system APIs to do so on the Hadoop input and output formats. What Spark did is it's basically using the same set of APIs for storage and I/O. So you can basically replace your compute engine with Spark and have access the same data set from all the sources which Hadoop supports. So that was a nice thing. Spark's abstraction, like the abstraction is called as an RDD. It stands for Resilient Distributed Datasets. I'll give a demo of what is the RDD at a later point. Like we'll look at some of the examples there. So it's basically a immutable collection of objects which is partitioned and distributed across multiple machines. So you can think like a distributed collection of objects. So that can be considered as an RDD. For example, if you put a data set in HDFS partitions the data into blocks and places it into multiple machines. You can consider this HDFS data set as an RDD. Like you can load it into an RDD using a Spark program. And once you have this distributed data set, it gives you these functional APIs like map, filter, which can help you transform these data sets into different data sets. So you take a RDD, you apply these transformations, and you change it into a different RDD and so on. And you can also do some actions that actually trigger the job itself. For example, once you have done the transformations, you can save the output back into some external location like Cassandra or a text file or HDFS, or you can get some results back into the driver program which you can analyze. So it has some actions. And one of the nice things about the RDD abstraction itself is the persistence is controllable. So when you load a data set as an RDD, you can specify what is your storage level. You can specify, I need to cache the whole data set in memory or on disk or a combination of memory and disk and so on. So it gives you a persistence level, and depending on the type of job that you do, like you can choose the data persistence there. And another thing is, since these are immutable, every time you have a source RDD and you mutate into something else, like in a different RDD, so you basically have a graph of all the changes from the source actually. So in a distributed computation, things can fail every now and then. So if RDD is lost or if some partitions are lost, these RDDs have information about like how it is constructed from the parent. So it can track this lineage and go and recompute it back. So that's how Spark provides fault tolerance at this point. Okay, so here's a quick example which is very commonly used. I guess you must have seen, a lot of you must have seen. So the diagram on the right shows like there is a driver or a master kind of a node, and there are 3 workers. And there is a data set, HDFS data set, which is partitioned into 3 blocks, like block 1, 2, and 3, which are residing in each of these machines. And what we are doing is we are writing a Spark program where filtering, we are reading this data set as an RDD. This lines is actually a RDD object, like it's an RDD abstraction. And we are filtering all the lines that begins with this word error in it. And we are also splitting it by tab and picking up the 3rd column. And the resultant data set, we are caching it in memory. So all these workers have something called block managers, which help you store the data in memory as a cache itself. So what it does is it reads the data, it does this transformation, and then the transformed data set is cached in all these 3 workers. And now you can fire multiple queries against this cache data set, which is like cache messages. In this case, we are doing a couple of searches, one for foo and the other one for bar right now. So the driver is a place where this program is running, where it's broken into tasks. For example, what would have happened is in this case there were 3 blocks. So Spark would actually spin off 3 different tasks. Task 1 will be running in worker 1, which will read from the block 1, do the filter and the map, and the result of it is cached in the worker 1 itself. And similarly, the same thing happens in worker 2 and worker 3. And so this is how it does the distributed execution. In this case, this example is simple, like there was only map where everything is in parallel. Like if it involves a reduce stage, there will be a shuffle in between. So, which is similar to MapReduce.
Good question.
Yeah.
Like, so there are two counts, two actions, right?
Yes.
So like, will it do like, so two actions?
Yeah.
It launches two different programs, like. Will it
Yes, it's actually sequential right now.
Yeah.
So when you do this first count, it'll launch
I
a
see.
task, for example, at that point, which will read those data sets.
Right.
So what it will do is when you hit the first count,
Yeah.
it will actually send 3 tasks to these workers. Each task reports its local count.
Yeah.
Then it will report all these counts to the driver, which will aggregate the count and show it back to you. If you want to run 2 things in parallel within a single Spark application, you can do it. You have to create multiple threads and call actions in parallel. That's how you can do it right now. Okay, so that's a quick introduction. I think I'm going to jump into Spark on Cloud. Before that, I can take some questions if you have at this point, or I can do it at a later point also. Yeah, yes.
Could you go back one slide, please? At any point, do you see that if there are data dependencies between the 3 blocks, how does the memory management work?
Okay, so there are no block level dependencies itself.
Okay.
For example, if you are doing something like so all these are parallel operations, there is no dependencies in this case. Let's say if you are doing something like a reduce operation, where the reduce operation is reading data sets. So in Spark and Hadoop world, you do actually reduce by key, where you have to bring in all the data sets that belong to a key to a single place, where you run the reduce task itself.
So would it then use the memory management in the
Yes.
the reduce module?
So there will be a shuffle involved, but the input data set is still read from the memory right now. There will be a shuffle involved. Anything else? Yes.
What does you mentioned tachyon? What does it do?
Tachyon. Tachyon is like a distributed in-memory file system. So, like I mentioned, like RDD has controllable persistence, right? Where you can cache it in memory or on disk. There is one more level where you can cache it off heap, basically. It's more like a. So the current architecture that I showed you here, in this case, the cache is actually part of the worker process itself. Where there is something called block manager where it is caching. You can also have tachyon running in all these workers, which is like an in-memory file system distributed across these machines, and you can cache it on the tachyon itself.
But tachyon is handled by the file system that is different, right? Not tachyon.
What is it?
Tachyon's distribution
Yeah.
of the cache,
Yeah.
distributed cache management.
Okay, yeah, I'm not sure about the distribution part, but one place where generally people are interested about tachyon is, so these, once it, for example, like we cache these messages data set as cache messages, and this cache messages RDD object is available only within the context of this application. So you cannot basically cache a data set and make it available for multiple users who can write their own application against it. So those type of users, what they do is they actually try to put it in external storage. If you put it in HDFS, it becomes a cost of reading from the disk again. So in that cases, they instead use tachyon to put it into the tachyon. Okay, one more question.
Do you have a recommendation on which cluster manager works better with Spark?
I think it's a hard question. Like the easiest, if you're starting with Spark, I would say standalone is the easiest to start with. But in Qubole, we are running Spark on Yarn right now. With Yarn, there are a lot of gotchas to make it work very well on Yarn. But I think once you get past it, Yarn is pretty stable after that. I don't have experience on Mesos, so.
Yeah, I asking because on Mesos it's given us a very long time as well. So.
Okay, so I think we went through the, so even in Yarn, it's not very easy. There are a number of gotchas, so when you're initially setting up, you have to get through all those things. Once you've gone through that, I think it's pretty fine with it. So,
I think the blocker account is schedulers.
what is it?
There's only one scheduler that's available. And
In-
you don't have any hierarchical queuing or
Okay, okay. Is there some kind of fast scheduler also in Mesos?
no, just the VRs.
Okay.
Other than Mesos.
So, not sure much on Mesos, but Yarn has been like once you get past it, it's pretty stable. Yeah, I haven't seen any Yarn related issues as such. Other than Yarn kills your container if you take too much memory. Yeah.
What are the gotchas of?
What are the gotchas? The Yarn Spark
Yeah,
and
slide on that.
I don't have a slide on that. Okay, so I can give some idea. I don't want to talk too much, take too much time there. So Yarn has number of properties. So you'll basically have a resource manager sitting in one of the nodes and node manager sitting in all the nodes. Node manager has a bunch of configuration like what is the total amount of memory that the container can use in this node, because the rest of the memory is required for the host, operating system, and the other stuff. You need to configure that correctly. And it has additional properties like what will be the minimum size of the container that it can run, or what is the max size of the container. Usually, I think what we do is, like in Spark, you can request container of different sizes. Like you can request an executor of 30 GB also. So it's usually recommended to have these yarn configuration configured so that you can run the largest container possible in that particular machine. What else? I can't think right now, but I can maybe I can think and get back to you. Like there are a number of things. Like at least there are like 5 or 6 configurations that you have to tune there. Okay, so I think I want to focus more on Spark on cloud itself, and what are the advantages and challenges that the cloud environment brings in, and how we have solved it in Qubole right now. So the easiest way to get started, I just wanted to get started with how do you do it yourself if you're on the cloud. So for this talk, I'm going to just assume the cloud is AWS. Most of it applies to other clouds like Google, Azure, or anything else. So the easiest to start with is you can install Spark, and easy to, you need some kind of a tool which spins up a cluster of instances. You need to choose the backend, which backend that you want to use, and you're all set. You can actually go and submit your Spark jobs. In fact, there is a much easier thing. There is something called Spark EC2 script. Not sure if you have used it. I think if you want to get started with Spark, probably this is the easiest starting point. All you need is an Amazon account, you need Amazon access and secret keys. Once you have it, it helps you spin up named clusters. So you can say Spark EC2, give me a cluster of size 10 nodes, and you can name this cluster as something. Yeah. And it's pretty good. I mean, it does all the hard work for you. It's in Amazon, it sets up the security group, it spins up instances, it installs Spark, it gives you back a working Spark installation for you. So this is a good starting point if you're thinking to get started with Spark itself in a distributed fashion. If not, you can do it on the local mode anyway in your machine. The nice thing about this script is it has a number of things, it helps you choose instance types, availability zone, Spark version, and so on. So it's pretty good starting point. So I want to switch to the cloud-specific advantages. This, this applies to other big data tools also, like Hadoop, Presto. It's not Spark only, but I'm going to cover some Spark only aspects here. I think the first biggest advantage of being on the cloud is you can use your object store as a data lake. What I mean by this is in a typical data center environment, you usually have a Hadoop cluster which has a HDFS running in it, and you dump all the data into HDFS right now. So you are somehow limited to the size of the HDFS. And since the task, MapReduce task also runs on the same set of machines due to the data locality requirements, you actually have HDFS and MapReduce running on the same set of machines right now. What this, the problem is, in this case, there is a scaling problem. You may have a lot of data, but you don't have that much processing, but in this case, you may need to have a lot of machines. You may have another case where you have very limited, lot of processing, but very little data. So you may run into these issues. So the best way in cloud, what you can do is you can actually separate the compute and storage. You can just put all the data into S3 and spin up clusters whenever you need, basically. So that's the main advantage of being in the cloud. And S3 is highly available and reliable. And from our experience, 3 to 4 years in Qubole, we have never heard of an object loss in S3 so far. So it's highly cost effective. I think a lot of people are concerned about the performance difference with respect to HDFS versus S3. In our experiments, we haven't seen a very big difference. Usually S3 is slower by an order of 10 to 15% compared to HDFS, not more than that. And since there is a native S3 file system, which is a file system API for S3, you can actually use S3 as a like a Hadoop distributed file system itself. So you can read and write using the same set of APIs. For example, from a programming standpoint in Spark, it doesn't matter if it is an HDFS or S3. When you specify a path, it correspondingly figures out the right file system objects and does the IO for it. So that's the first advantage. A follow-up of that is what that enables you is you basically need not have a cluster running all the time in a cloud. Because your data is sitting in S3, your data is not in HDFS. So you can spin up a cluster only when you need it. So let's say I have a job that I want to run on a particular data set. I can actually launch the cluster at this point, do the processing, and write the results back to S3 and shut down the cluster. So I can keep the cluster up and running only for the amount of time that I need. And another thing that this enables is you can actually have multiple clusters. So in a large organization, usually like there are a lot of groups of people, and each group wants to have an individual cluster so that like you don't contend for resources. Otherwise, it becomes a big problem if everybody jumps onto one cluster. So if you have data in S3, what you can do is you can actually spin up your own cluster for your own team based on what requirements you have. In fact, like Netflix gave a talk at Spark Summit where they are actually spinning up a separate cluster in EC2 for every Spark job that they submit. I think although it's very simple, it's not the most efficient thing, but I mean that gives the idea, right? Because they have the data in S3, you can do this. You can basically spin up when you need it, do the processing and shut it down. I think the third biggest advantage of doing Spark and cloud is the flexibility. Like, for example, if you're on Amazon, you have a choice of a wide variety of instance types. I can use Spark for some use case like caching and querying, where I want to cache a huge amount of data set, like on the order of GBs or TBs, and then run some interactive analysis on this data set. So for these, I can use R3.4x large instances. If there are compute-heavy workloads, I can use C3 instances. This goes back to the previous point also. So I can have different clusters for different type of use cases, each meant where each instance is good for that type of use case. So you can do that. And there are other things like Amazon has pod instances where it actually sells the excess capacity using bidding. So you can get the instances at a much lower price than the regular instance that you pay for. So you can use these instances also for distributed computation. The only catch with pod instances, Amazon can take it back anytime they need it. So you need to do something to handle these cases. So I'll talk about something there. And some of these newer instance types in Amazon doesn't have a lot of disks, but you can always add EBS disk if you need more disk storage. I think the biggest advantage of being in the cloud is autoscaling, where it's a very well-known thing that most of the big data workloads are bursty. Like if you have a time series where you're looking at the peak workload across time, it will be very bursty in nature. Usually, like it will be idle for a lot of time, and then it suddenly bursts, and then it goes down again. So what happens is, like when it bursts, like a lot of users have submitted the job, it will end up being in a queue. The jobs are not getting processed quickly, and so on. And less of the times it may be idle, and nobody will be using those clusters. If you're in a cloud environment, you can deal with this problem by adding machines at runtime. For example, if there is more load, you can add more machines dynamically. If there's less load, you can release the machines. Although like this sounds interesting, it's pretty hard to do it in a very efficient way. So I'll talk about like how we have done it in Spark in the next section. This makes it very, very cost effective. So one is you are keeping the cluster alive only for the time you're processing. The next is you are actually using the right number of machines that you need at any point. The right number of machines is a little like you can argue like what is right number of machines, but yeah, we have a good enough metric. And so I'll talk about how we do autoscaling in Kubol. Okay, so now I'm gonna switch into like I'm gonna talk about challenges. Like so, we looked at 4 of the main advantages. One is like you can use S3 as a data lake that enables you to spin up like clusters on demand, like ephemeral clusters, multiple clusters. Cloud gives you a place where you can configure it differently based on type of workloads, or each team can have a different clusters based on the needs. And the 4th is you can actually do autoscaling, which like you can actually scale the cluster up and down based on the job load itself. So I'm going to talk about like how we have solved these challenges in the cloud a little bit, and I'll also show a demo of Kubol. At the end of the talk, like I'll give a username password so that you can try whatever I'm doing it here. You can actually spin up clusters, you can submit some jobs, and you can see those in action. So I think the first thing that you have to do, like for the ephemeral clusters, you need to have some sort of a library that can spin up clusters. So that's a minimum requirement. Now, so one starting point is the Spark EC2 script itself. You can use Spark EC2 script itself and build a layer on top of it to spin up clusters on demand. So what you have to take care in addition is the clusters go bad every now and then, like some machines go bad. So you need to have some sort of automated tools which can figure out these bad machines and remove it from the cluster. And sometimes, for example, when you're running on Spark and Yarn, like RM is a single point of failure. You may have RM in memory pressure or something where the RM process dies. So you need to have mechanisms to figure out these kind of cases and restart the cluster for these things. Or if possible, you should be able to take action. So these are more like you need to build a set of tools that helps you auto heal when the cluster goes bad in a cloud environment. So at Qbol, we actually provide something called a control panel where we make it very easy to spin up clusters on demand when you need it. We use a library which is forked from MIT Star Cluster long back, and we have added the cluster lifecycle ourselves on top of it. And so I'll just show a quick demo of like how easy it is to spin up clusters using Qbol right now. So I'm logged into Qbol. Qbol is a big data as a service platform on the cloud itself. So I'm looking at something called as a control panel. The control panel is a place where you specify all the configurations of the cluster itself. So here I have multiple clusters running. For example, I have Hadoop 2, Presto, Spark, and some demo clusters running. So if you want to create a cluster, all you need to do is you go to this cluster label. You can specify something like whatever it is, Spark demo, and you can choose the cluster type as Spark. And we allow you to specify the Spark version that you want to run, like 1.5 or 1.5.1. Let's say I want to run 1.5. And I mentioned about autoscaling, where the Spark jobs will autoscale. I'll talk about like how we do that. That's why we have this minimum slave count and maximum slave count. So you can actually start a cluster with just like 2 nodes or whatever it is, a new number of nodes. And you can also specify a max. So depending on the load, we can add machines at runtime and then remove machines when you don't need it. So you can specify a min and max. For example, I'm saying like I just need a cluster of size min 2 nodes and max 10 nodes. I can choose the machine type. So let's say I need amount or X large. I'm not going to run any heavy stuff right now. And it also has lot of these configurations. So all the configurations that you want to do in Amazon is basically available in this page. For example, if you want to launch a cluster in a VPC, so you can specify a VPC and a subnet where you want to launch a cluster and so on. And we also give you ability, like we have some recommended Spark configurations for each of the node types. This is an interesting thing. Like each node type is very different. So as a service provider, like we want to make it very easy for the users to have the default configuration. So we have a very good default configuration for both Yarn, Hadoop MapReduce, and Spark, which is based on the instance type. So you can override these things if required. So once you define all these cluster policies, so once you hit save, you're not spinning up a cluster at this point. You're just saving a cluster policy, like how do you want a cluster. For example, so I have saved a new cluster called a Spark demo. It's not running right now. If you want to spin up the cluster, you just hit this right arrow here and it'll spin up the cluster for you. Since we specify the min nodes as 2, it will spin up a single master node and 2 slave nodes for you. With Qbol, I think when you're trying it out, you don't need to explicitly spin up the cluster also. What you have to do is when you submit a Spark job, you specify what is the cluster that you want to submit to. So you can specify I want to submit to Spark demo and Qbol will automatically spin it up for you. Also, we have this auto termination. So a lot of people actually spin up a cluster and forget to terminate it. It's a very common problem in the cloud because we are spinning up multiple clusters per user right now. And what Qbol does is it can automatically terminate. It can look at the cluster, whether the cluster is heavily loaded or not, and it can terminate if the cluster is like idle and so on. And it also takes care of small things, like for example, if you are launching a machine in Amazon, you have already paid for the complete hour, so it makes sense to keep the machine for the hour itself. So we wait till the hour boundary and then wait till the instance and so on. So let me spin up a cluster for this. So I'm just starting a cluster right now. I think at the end of the demo, I'll just set up multiple clusters so that you can just try it out on different clusters. I think if everybody uses the same cluster, then it may have some issues, unless like the cluster is really big. So so it will come up in some time. So meanwhile I'll go back to the slides. I think so. I showed you like how easy it is to spin up clusters and configure it in Kubol. So the next thing that you need is once we have a cluster, you need different interfaces to submit the jobs to these clusters, right? For example, there are data engineers who might be building some machine learning or a graph processing program in Scala or Java. They need some sort of API or SDK to submit these jobs. Like they don't want to come to the UI and submit it, so they need an API-based interface. And usually these type of engineers, like, so you actually build a library of programs like Scala, Python, PySpark programs. So usually what people do is they bundle them into a jar and have this jar living somewhere in a persistent location. And all they need to do is they want to give a Spark submit command line if you know what I mean. That's the starting point of the Spark job. So we also have the ability to specify the Spark submit command line itself. So that's a data engineer. And we have a persona of users called data analysts, like who don't understand the programmatic way of dealing with things. They just want a SQL-based interface to do some large-scale computation. So what we expose is we give them what we do is like Spark itself has something called as a Hive thrift server, which exposes the SQL interface for you. It's a JDBC endpoint. So you can use WL mode and connect to the JDBC endpoint and fire the SQL queries. So data analyst needs this type of interface. The data scientist needs more of a notebook style of interfaces, like more like a IPython style interface where you can do something and get the results back inline in the browser itself. I think this has become really interesting recently, and one of the nice things about Spark is like all the languages like Scala, Python, they are like interpreted, like they have a shell-based access, so you can basically make them available in a browser environment. Basically. So I'm going to show a quick demo of how you can do this in Kubol. So let me go to. I'll just start with a data engineer case where he will submit a Spark job. In Kubol, we have something called as analyze, where you can specify a wide variety of jobs. We are just looking at Spark command in this case. You can actually run a wide variety of big data workloads in Kubol. And you have a choice here, like I can run a Scala code or Python code, or just specify the SQL itself, or you can even run Spark R here. So we give a simple text editor, where you can just copy paste your program. It's not the place to build your program itself. You can build it in your IDE and just copy paste the program here. So just to show you an example, so I'm just doing SC dot parallelize. I'm just doing a one-on-one example here, and so I'm just taking a list of integers from 1 to 10, and I'm just collecting it back. So just to show you like how you can run a Spark program through this interface. So you could see that it already filtered out the Spark clusters that are available in the control panel and showing you these options. There are things like demo 1 Spark and Spark demo. Spark demo is a cluster that we recently created right now. So I can choose which cluster to submit to. So when you're trying it out, I think I'll create multiple clusters for you. So some clusters might be like, since I'm just creating a cluster of size 5 nodes, if multiple users have submitted jobs to it, your job might be in queue. So just pick a different cluster and just submit to that thing. So I'm just picking Spark demo here and just hit run. And one of the things that we do is like we immediately fetch the logs of all the jobs and show the logs in this UI itself. So you will see the logs of the Spark application. Since we have provided the Scala code itself, we have to actually compile the Scala code and build it into a jar before we launch the Spark program itself, right? So we do all the things for you. Like so, you could see that we are actually compiling using Scala C and then building the jar for you. It's like a easy to use thing. Like if you want to get started, you just want a simple interface where you can just write things. So you can use use this API for that purpose. And it will also show you the complete Spark logs itself. Since we are running Spark and Yarn, it will launch a Yarn application, submit this job, do the processing, and get the results back to you. So I'll also submit. I think let this go on. I'll submit another job in parallel. I can just submit a SQL job this time. So one thing is with Qubole, like since it is an as a service offering, like everything that you do through our UI or API, all these commands are captured in the databases. So you have the complete history of all the jobs that you run through the interface. So if you run a job, you can basically go to this job and look at like how the job did, what are the logs and results and so on. You can go back in history and check the results and so on. So for example, I'm doing a compose again. I'm just creating one more job and just doing a show tables. Spark SQL has a nice thing where you can actually talk to your Hive metastore and can access all your Hive tables itself. Spark itself doesn't have a metastore like Hive. So we are running Spark SQL against a Hive metastore in this case, like a Hive context. So this will basically list down all the tables that I have in my Hive. So where it helps is a lot of our users actually have a number of Hive tables already created, which is like pointing to some data set sitting in HDFS or S3. So you can actually take some of these Hive queries and just run it using Spark SQL backend itself. So this is a very nice way of getting into Spark itself, I think. Although I'm not sure whether it can handle the complete capabilities of Hive and the scale at which Hive can deal with things, I think it's a good starting point there.
So quick question.
Yes, yeah.
So that Hive tables, does it just treat them as raw files and like not run Hive server?
So what it does is it talks to the metastore,
right,
fetches the table and schema information and where the data lives,
right,
and then just passes everything to something called as a catalyst, which is like a Spark SQL
I see.
compiler and optimizer,
Right.
and then it uses Spark core engine itself to submit it. The only interaction point is the metastore.
Right.
The other things are like if you have Hive UDFs, I mean that's another interaction point. Other than that, nothing else in Hive.
Okay.
Yeah. Like you can reuse the Hive UDFs itself in Spark SQL.
Okay.
Yeah.
Cool.
Yeah.
So this is you recommend to use Amazon S3. Do you happen to also have a demo using say Cassandra?
I don't have a Cassandra cluster in my Amazon environment right now. But if you have, I mean, it's not any different. Like, if you have a Cassandra cluster, I think Spark has API values say like how to read data from the Cassandra. It will basically have some kind of a connection information like how to connect to the Cassandra cluster, what's the endpoint, and so on. And you must be able to connect it. So, not any different, I think. Like, it depends on what you want to program it. Like, if you are writing Scala code, you can just write Scala Spark plus Cassandra code here itself in this editor. And as long as you give the right connection parameters, like it will be able to read from the cluster and process it. So I see a lot of people using Spark for processing the data and dumping the data into Cassandra itself for some real-time consumption. So that has been a very common use case. Okay. So I think like I just had a couple of Hive tables in my account, so I just got those Hive tables back in this UI. So you could see that like when you're running, let's say if you're trying out certain large jobs, you may want to configure like how much containers it needs or how much memory you want to allocate. So one thing about Spark is unlike MapReduce, Spark you need to specify the resource allocation when you submit the job itself. So for example, let's say when I'm running on Spark and Yarn, when I submit a Spark job, I have to specify how many containers I need. I might say something like I need 2 containers, and each container should be of size like 10 GB and can use 2 cores and so on. So you need to specify all these configurations when you submit the Spark job itself. Since we have come up with some sort of defaults for machine type, it didn't ask you for any of these configurations. But let's say you want to try out something, a larger job maybe, you can actually edit these configurations. So you can override it and say, so num executors is something which says like the number of containers that you need for your program. So you can say I need 10 containers, each of size 2G and so on. So you can specify these configurations from this place itself. Also, I mentioned like a lot of people actually bundle all the programs into a jar. In that case, you can use this command line and specify the Spark submit command line. Like because a lot of people have bundled it. In that case, you just specify the command line itself. Like all these other interfaces like Scala, Python, or the language interface are useful if you have a small program. What happens is as you build out, like you have a huge amount of programs. Like a Python PySpark file depends on a number of other Python files. In that case, it's like you actually bundle them into something and then trigger it using this command line option. So that's the thing for the data engineers. I think what you can do is if you hit this analyze page, I would have run a sequence of jobs. You will also be accessing the same account that I have right now. I'll give the password for this. So you'll be able to see my jobs itself if you want, like just go change and play with it with these jobs itself. Right. And okay, so the next is like I don't have a demo right now for the tabular mode type of access. The next thing I want to talk about is notebooks. For data scientist use cases, like they want some kind of a IPython style notebook interface to do some processing. So I mentioned like there is control panel which is like where you configure all these clusters. So you could see that the Spark demo cluster is already up and running right now. It just has 2 nodes right now. It's running for 8 minutes. And I can access the Spark notebook which is available here. So you can hit the Spark notebook. And this will take you to a page where you can create notebooks, view all the notebooks that you already have. So just to give you a sense of like what all you can do with the Spark notebooks. So here is an example node. So you can do a few things, like you can write some Spark SQL itself, you can do some PySpark, you can write Python code, you can also write some arbitrary shell commands. So you can do some documentation also. For example, you could see that I'm running some sort of Scala Spark by example in this notebook. The good thing about a notebook interface is it runs the program and gets the results back and displays it in the browser itself. So it becomes a very good interface for building the application itself. So if you're doing it for the first time, I think this is a very interesting place to start with. So the example node has a bunch of hello world type examples that can help you get started. So if you're building your own notebook, you can just look at the examples here just to get started with Spark. So as I said, like there is Spark SQL also, so you can specify mod SQL and just issue your SQL statements directly. Or you could use the regular Scala way of doing things where you write Scala code to actually fire the SQL right now. The nice thing about this notebook is it has some inbuilt visualizations. So if you run SQL queries and get the data back in some sort of tabular fashion, it can give you a wide variety of options like histograms, bar charts, where you can plot some of these graphs right now. This notebook is actually something called as, we took something called Apache Zeppelin, which is an open source notebook interface, and Spark is well supported in Zeppelin, so we are making that available as part of our interface right now. So you can run SQL jobs, you can do some configurations, and the nice thing about this Zeppelin-based notebook is you can mix and match languages even within a single notebook. So I had Scala and SQL code before. You can also mix and match some Python code, like you can also run some PySpark code in the same notebook right now.
Do you write R code?
Right now, it doesn't have an R support right now. It is something which is out there in the open source, which we haven't pulled yet, so I think it will be available in a couple of weeks.
Do you support the Jupyter notebook? Or?
No, not right now. We just support the Zeppelin-based notebooks right now. I think, so yes, I think that gives an idea. Right? So you can basically use this as a place to build your Spark programs, and it's a very good experimental workbench to try out something. I'll basically show a demo at the end, like where I can talk a little bit about, like we can talk about what is an RE and do some simple examples in the end. So I think, so let me go back to the challenges. So that's the part 2 of the challenges. So we had the clusters, now we have the APIs for different sets of users. I think the next is the interesting part. How do you autoscale on demand dynamically at runtime itself. So Spark job has static resource allocation. Like when you actually start a Spark job, you specify like I need 20 containers of 5 GB size, and we can use 4 cores. So you specify a configuration when you start a Spark job itself. And what it does is, like in this case, we have 20 executors. So each executor is basically a long-running JVM, which just runs for the lifetime of the application itself. And these executors can run tasks. Like there was a central driver, we saw the earlier picture, right? The driver is a place where the DAG is executed, and it will submit these tasks to these long-running JVMs called executors. So executors can actually run multiple tasks in parallel. If you use a setting like executor cores of 4, by default it can run 4 tasks in parallel. So this has been the state of Spark for quite some time. So the difficulty in doing this is when you are submitting a job, you have to specify the resource requirement. It's a really hard problem to find because you don't know how much. For example, let's say you're caching a data set, you don't know how much the in-memory cache will take. In Spark, by default, it actually caches, like it's an on-heap cache. So it takes in all the objects as Java objects. So it loads your size. So if you have a data set of size 2 GB, if you cache it properly, it will end up around 6 GB to 10 GB in memory cache because of the Java object overhead. So it's really hard to figure out what is the right amount of memory required or right amount of executors for enough parallelism in the job. So what we did is like we actually plan to add Autoscaling, and we contributed these APIs to the open source right now. So open source Spark also has all these APIs where you can request and release containers when you're running a job itself. So in a Spark job, like SC is something like a Spark context. That's a starting point of a Spark job itself, so where it's like an environment you have set up and you can run stuff on it. And within a job, now you have the ability to ask for more containers. So you can request, I need 10 more containers right now. And you can also release some containers. Like I don't need, for example, let's say I'm done with the processing, it's idle, I can release the containers. So the first thing that we did in Autoscaling is build the APIs which can request and release the containers. And once we have this, now the next thing that is required is we need a mechanism when to add and when to release. We need an automated way of doing this. So one is programmatically, you can yourself do this. Like if you're running Spark and Yarn, you can do this. And I think there's support on standalone also, not on Mesos, where you can dynamically ask for executor or release executor right now. The next thing is now we have the APIs. Now we need to do something like how do we autoscale now? So if you know Spark, what happens is like a Spark program is basically broken into a set of stages, and each stage basically runs a number of tasks, something like 20 tasks or 40 tasks. There is a configurable number of tasks that runs in a stage. So what we can do is at runtime, we can keep monitoring how the task is progressing. And once the task completes, we know how long the task took, right? So we can actually come up with the estimated runtime for the whole stage itself. Because so there are only 2 parameters. We know the number of tasks within a stage, we know how long one task took. So for example, let's say if we have had 1000 tasks and we had only enough parallelism to run 10 tasks at a time, after these 10 tasks are complete, we know like what is the average runtime of a single task, and I can compute how long the stage is going to take. So now I have estimated time of this stage completion. The autoscaling algorithm we have written is like you can set some sort of ETA, something like my stage needs to complete within some certain minutes. So you can say something like my stage has to, every one of my stage in my Spark job has to complete within 2 minutes. And in that case, what it does is it figures out like how many executors that it needs, like how much parallelism it needs to actually complete this particular stage in 2 minutes time. So depending on this calculation, which is pretty straightforward, it actually goes and requests for more executors at runtime, and the task gets spread across a wider number of executors. And once it is complete, let's say the stage doesn't need that much amount of resources, it can actually go and release these executors back. So that's one way to autoscale. We also have a memory-based autoscaling. For example, the first use case I mentioned is like you don't know how much a cache data set will be in memory. So what you can do is, in this case, without worrying about it, you can just specify a min containers and max containers when you launch a Spark application. And it can monitor the memory. If the amount of memory within the Spark job available for RDD caching falls under a certain threshold, it can start adding executors. So we actually have a memory-based autoscaling algorithm also here. And so upscaling is pretty much fine, like you can add stuff like when you need, but downscaling is extremely hard. I think this is the hardest part in Spark right now. The reason being, like, the executors have a lot of state information, like you may have cached RDD. In that case, like it has some partitions cached in those executors. It may have some shuffle data. Let's say you have a lot of stages, so it may have some shuffle data living in those disks, so the executors know where the shuffle data lives. If you lose the executor, you are losing the shuffle data also. So you cannot basically, like, even let's say the stage is complete and you don't have enough tasks to keep these executors busy, but you cannot just kill them, because if you kill them, you're losing all the cache data and the shuffle data that is living in the executor. So this is a hard problem to solve in general. I think one small step is to use external shuffle service, so that you are actually moving the shuffle data out of executors to something called as a yarn auxiliary service. But still, even after doing that, you have the RDD, cached RDD problem. I think one small way where you can do this is you can actually cache it with replicas. Like you can have each partition of the RDD sitting in multiple machines. In that case, you may actually pull down one executor, like you may have some partitions living in other machines. So you can do that, but that has a cost because you're replicating your whole cache data set again. So that's a hard problem. I think if you want to really solve it, you have to, compress the cache into minimum number of executors which can hold it, which is slightly hard in Spark at this point, and it's not available right now. So that's autoscaling. So any questions so far? Okay, so I mentioned like you can specify these configurations, right? To enable autoscaling, what you have to do is, in addition to these num executors, you can specify something like max executors. It says like the max number of containers that this job can have. So you can have a job which starts from 2 containers and it can use up to 20 containers. So the parameter is called max-executors. So if you do the autoscaling, it will be enabled and it will determine anything based on the algorithm that I just mentioned. Okay, so the next thing with respect to doing something Spark on cloud is debuggability. Like we talked about all the nice things about ephemeral clusters, like we can bring up clusters when we need it and shut it down. But the cost is now, let's say your job has failed, now you have shut down the cluster. I mean, you need to have mechanisms to get to the logs, to get to the Spark application UI so that you can debug things. Like debuggability becomes hard in ephemeral clusters stuff. If you have always on-running cluster, you must have all the debugging information dumped to some location, either to the logs or to HDFS, so that you can go and get back to them. But in ephemeral cluster, there are some challenges. So what you need to do is, there is something called as a Spark history server. Like, have you seen Spark application UI? Like application UI is a place where you can see like how the job is progressing, how it is broken into stages, how many tasks it's executing and so on. And so you can run a history server actually inside a cluster, but if you pull down the cluster, you actually lose the history server also. So you need to have some kind of a history server which is running outside the cluster so that you can render the UI. And Spark generates a lot of event logs that helps you in rendering Spark application UI. For example, let's say your application failed, you can go to Spark app UI and see like when your executors got released, when the stage got completed, what are the error messages and so on. All these are dumped as event logs in HDFS. So since if we lose the cluster itself, we don't have HDFS there. So we need to take care of like copying all these things to S3. We need to do like continuous backups of all these log information. So in Kubol, what you can do is, even if the cluster is shut down, you can actually get a link to the Spark application UI that helps you debug all the information. For example, here is a link to the Spark application UI itself. So you can see like how the job is broken into stages and how the job is progressing overall. And we make sure all these logs and events are copied outside of the cluster in S3 or some location so that you can look at these UI even after the job is completed. So I mean, this just to show, like, you can see things like what are the number of executors, how much memory it used. It also has, links to these executor logs, like what these containers are doing. So the container logs are available here. And it also has like this storage tab, which is interesting. Like, if you're caching a lot of data, I mean, in this case, I just did a show table, so I didn't cache any data. This storage tab will actually list you all the RDDs that you have cached, how much it is cached, and how much memory is available, and so on. So when a Spark job fails, what you need to do is you need to go to these logs, figure out the Spark application UI, and just go debugging from there. Okay, so that's the debuggability part. So another thing, one small catch with S3 is all these big data tools like Hadoop or Spark, when you write a job where you're writing the results back to S3, what it does is it writes a data to some temporary location and then finally it does a move to the final location. But unfortunately in S3, a move is a very expensive operation. You actually copy all the data back to a destination and then delete the original data. I mean, in HDFS it's just a rename operation. In S3 it's not a rename operation, it's a very expensive operation. So if you're working on cloud, it's recommended to use something like direct file output computer. It's called DFOC, where it will write the results directly to the destination instead of writing to a temp location and doing a move. So this usually gives you a lot of performance benefits. We have seen that the job completes in a short time frame, but it ends up writing to this temp and doing a move, which is very, very expensive. Instead, you can use DFOC and write the results directly to the destination. Okay, so the next is spot instances in Amazon. I think with spot instances, it gets very, very tricky. Like for example, in this case, we'll have some workers or some Spark executors running in these spot instances. So if we lose these executors, we'll lose the cache data. We'll also lose the shuffle data. But Spark can actually track lineage and actually recompute the lost things back. That's the fault tolerance part of it. But it's very inefficient. What we have seen is like if you lose a large number of executors, it can actually get into a cycle of recomputing the previous stages, and then you have a lot less resource now. It fails, so it will go and recomputes. The cycle iterates a lot. So I think it's a hard problem in general with respect to spot instances, like how you can do it in a reliable way right now. But there are some use cases where you can use spot instances. Like, for example, these are not production workloads. It's fine if these workloads fail. In that cases, you can actually spin up a spot cluster, which is like 50% of the on-demand cluster in Amazon. And most of the Spark workloads are very short running, like in the order of minutes. Unless you can have a long-running job, but for these workloads, you can just submit it in these spot clusters, and you may not actually lose a machine when the job is running. So you can actually get the job done with just spot instances. And since the jobs are short running, if in case there is a failure, you can actually go and retry anytime. So there are some places where spot-based clusters is actually useful. So in Kubol, I showed you a control panel where you can configure it. You can specify I need a spot-only cluster where all the machines are like spot instances. In that case, you are saving on cost. So it's another nice thing where you can save on cost. So another thing that is commonly required right now is something called Spark Job Server. So I mentioned the RDDs which are cached in a Spark application is only available within the context of their application unless you use something like Tachyon, which is external to the application. So a very common use case is people want to cache it in memory and make the cache data available across a lot of users. Right? So where one guy starts a job which is doing some transformation and cleansing, and this cleansed data or aggregated data should be made accessible to a variety of users. This is actually not that easy in Spark because you need to connect to the same application to submit it. So for these type of use cases, you need something called as a Spark Job Server, where it can actually keep the application running for a long time, and it can give you a REST-based APIs to submit snippets to it. So you can cache a data set in a Spark application, and multiple users can actually go against the cache data set using some REST-based endpoint. So you need tools like Spark Job Server for those type of use cases. I think that's what I had in terms of challenges. Maybe we can do a quick demo on the notebooks. I can just talk about what is a RDD, and I can talk some maybe I can take some machine learning example and just demo it to you. I'll basically share the details after this demo so that you can also try it out after this. Okay. So let's get started. So I'm creating a new notebook. I'm creating something called workshop. Okay, so I'm creating a new notebook. You can create multiple notebooks. So when you use the notebook interface, make sure like you create your own notebook. So I'll start off with some examples of how you can use this notebook. So I'm going to program in Scala, but whatever I do, you can do the same in Python also. It doesn't support R right now, so you can either use Scala or Python to try it out. So I can start something like, for example, I'm just creating a list of integers in Scala. This is an interface to create. I'm just creating a list of 3 integers. For the first time, what it does is it's actually launching a Yarn application because we are running on Yarn backend. So there is a small overhead in launching the Yarn application. It usually takes around like 20 to 25 seconds to launch it. But once the application itself is running, it's interactive. Like you can fire queries and get the results back in an interactive speed. So you don't need to list it down. Like once I give access, you will be able to see this notebook also. So you can actually check this notebook and you can try it out on your own notebook also. So so what I thought is I'll just introduce the concept of map and reduce in a single node environment, like in a Scala itself, and then introduce the concept of RDDs, like how this is extended to a distributed environment. So we just created a list of integers in this Scala, and Scala gives you higher level operators. For example, there is a higher level operator called for each, where you're just looping through each of these elements, and it takes in another function that says what do you want to do with each of the elements. In this case, I'm saying just print all the elements back to the stdio. So you could do some transformations too. Something like I can transform this input set of integers into a different set of integers. Let's say I am just doing a transformation where I'm adding 1 to each of these integers. So I'm just creating a new list of integers, which is just as where I'm just adding 1 to each of these numbers. So here, actually, this is a real map operation. Like we are doing mapping of one collection to a different collection right now. And Scala has things like higher level operators like filter. Okay, so just a quick note on the syntactics here, like what I did in the previous thing. It's actually map is a higher order function. It's taking in another function which takes in x as an argument. And the function body just has like x plus 1, which is a return statement of the function. So it's like in PySpark, the equivalent of will be like lambda x plus 1 in PySpark. So I can filter some things like, for example, I can let me expand this to a bigger data set so that we can. So I'm just taking the list of integers. For each number, I'm just creating a bigger list, like 1 to that number itself. So now I have expanded the list. I can call this expanded list as y. And I'm going to operate on this list right now. So I did a map operation, so I can do some filter operation where I can say the number is less than 3 and get those results back. So the nice thing about the notebook is you get the results back interactively. You can peek at how you're doing, you can look at some sample records and then keep building a program. So far what we have seen is all these are map-only operations where you're just taking a record and just transforming it into something else. And Scala itself and also other functional programming languages have things that can help you reduce this into a single number. For example, there is a reduce function, which is again a higher order function, that tells you, right, given 2 elements, how do you want to combine these 2 elements? So this is a Scala shortcut. You can think of it like there's a function which takes in 2 numbers and just does a summation of these 2 numbers. So what I'm saying is I'm just saying go and use this list of integers and what is the thing that you need to do between every pair of integers. So it just summed up into a single number, which is 6. So what we actually did is we did map and reduce itself, but we did it in a single machine. The only difference between this and the MapReduce and the Spark world is, in this case, the reduce is actually like a global reduce, where you're taking the complete collection and reducing into a single element. But in MapReduce world, you typically do something called as a reduce by key. So the output of the map operation will be something like a key value pair, where you design the key the way you want, like it depends on how you want to reduce the data. So let's say you have a data set which has like multiple columns. You may want to aggregate based on one column, so you will put that column as a key and you invoke a reduce by key function. What happens is there is a reduce that happens for each of the key, stuff like that. Let's say you have a data set which had country as one of the column, and you say reduce by the map operation, dumps something like country, comma something else, let's say. You can do a reduce by key where each of the country values gets into one reducer. So you will have all the data sitting at one place and you can do whatever you want in the reduce function. So this is basically where we created a collection of integers and we are transforming it, everything we are doing in a single machine. So let's do this in a Spark itself in a distributed fashion. That's where the RDD comes in. So let me create a bigger list, or I can, okay, so I can use the Y itself. So for doing distributed computation in Spark, the starting point is a variable called as SC, which is Spark context. So I'm saying Spark context dot parallelize this list. So I'm saying like take this collection Y and parallelize across the workers. So in this case, my collection is small, but it could actually have a larger collection also. So let me run this collection. So you could see that the result of this is actually RDD of integers. So we actually have created a distributed data set. So in this case, why is it distributed? Because by default it has a partition like parallelism set to 2. Like parallelize takes an additional argument, something like what is the number of partitions that you need for this data set. So if you have, let's say, 1 million records, you can say parallelize is 1 million records across 10 machines. Let's say you want 10 partitions, you can specify my parallelism must be 10 and so on. So I can specify something like, put this data set into 3 partitions. So if we have had 3 executors, it would have actually chunked this data set into 3 blocks and it would have placed in 3 different executors.
What happens if there are 2 executors?
So each executor actually can have multiple partitions. It need not just have one partition, like similar to HDFS. Like you can just have one node, you can still put a file into HDFS, it will still partition into blocks, but these are all the blocks living in the one node. So yeah. So we created a RDD of integers. In this case, it's just a distributed data set. So I can transform this RDD. So let's say I can do the same set of transformation here in Spark itself. In this case, it is actually doing a distributed computation where it's actually sending the same map function to all these set of workers, doing it in a distributed fashion and just showing you the results back. So I can pretty much do the same thing. So in this case, I can do this. And so if you see that if I run this thing, what I get is something called as a map partitions RDD. It didn't do any computation actually. So in Spark, all these operators like parallelize, map, for each, all these things are lazy operators. It doesn't actually trigger a job itself unless you perform some type of action. Let's say unless you want to get the data set back, it doesn't actually run the program for you. Because that helps you build the program itself here, and then once you want to run it, you actually trigger some kind of action with it. So what it has done is, if you look at it, there are 2 different RDDs. In this case, this map partitions RDD, right, will actually have this parallel collection RDD as a parent. So that's where the resiliency comes in. So if I mention like Spark as a DAG of operators, what you're saying is you're actually creating RDD and then transforming it. By doing the transformations, you're actually building this graph itself, the actual DAG itself. So in this case, let's say if I have cached this resultant data set into memory, right, and if I have lost the partition, it knows what is the parent RDD, and it can go and recompute from that actually. So it can always go and recompute. Usually, you don't actually parallelize a thing. You actually, the starting point of the Spark job usually is some external location like HDFS or S3, some persistent location usually. So even if you lose everything, you can go back to your persistent store and read it back. So that's like the starting point always. In this case, I'm just showing some small examples right now to begin with. So you can also chain these things. So I have a map partitions RDD, and I could have done something like I can chain all these things together. I could say like, you know, filter everything which is less than 3 and do a collect. Collect is something like an action which actually triggers the program itself. So right now I'm actually running a Spark job which is running this thing and actually collecting the results back. This is when the Spark job is really running right now. So that's a quick example. I think we looked at partitioning, we looked at the lineage by using resiliency, like how it tracks the lineage. We can also do something like caching right now. Let's say I had this data set in some variable z. I could actually cache this data set, like a result, into some thing. So, and then I can invoke some kind of a function like, you know, count, just give me the number of records here. In this case, it could have actually cached this data set in memory itself. And once you cache it, you can, you know, what are the queries you are hitting, you are going against the cache, so it will be really cached after. So if you're, for example, if you're loading some data set from some persistent location like S3 or HDFS, you can choose to cache it where, you know, it has computed something and cached the data set, and then you can just hitting the cache after. So we can, so this explains like how the caching works. So this is an example of, this is an example of caching here, but this count would have actually triggered the caching itself. So I'll show some examples where I have a simple data set, a movie lens data set sitting in S3 right now for this demo purpose, where I think the data set has 3 files, like a users file, a movies file, and a ratings file. It's a very common example in Spark machine learning. I have this file called a Spark movie lens, which is available in the Spark example itself in the Spark repo. We can do this thing, like I can run this program using this notebook right now. So what we have is we have users file where we have like some set of users and some details about like what the user likes and so on. We have a ratings file which is like user comma rating comma user comma product comma rating. So we have a tuple, like I think this is the data set which is made available at some point by some group called Movie Lens. I'm not sure about the source of the data set itself. We can do some machine learning on this data set right now. So I'll create some RDDs for these data sets. So I can say users, and my data set is living in this this location. So you will be able to access all these locations, like you must be able to run these programs. There is something called users.data. And if I run this, you know, it doesn't run anything. Again, it's a lazy operation. It just creates something called as a RDD object, which is like pointing to this location in S3. So similarly, I wanted to load the other 2 files also. I think I have a ratings file, which is what we are going to use for this demo. And there is some movie file also. So we'll see, we'll look at an example, machine learning, like how easy it is to use the ML APIs of Spark ML itself. Okay, so we have 3 RDDs, users, ratings, and movies right now. And these RDDs, again, like it will have a default partitioning of 2 partitions. So if you actually run it without specifying additional partition parameters, it will actually launch 2 tasks, which is going to read a chunk of the file from the S3. So what I can do is I can look at, like, you know, how does this ratings look like. So I'm just going to say ratings dot just take some 5 records and just show it back to me. So take is again another action that actually triggers a Spark job itself. So in this case, I took 5 records from this ratings thing. So let me print out in a nice way also. I'll just loop through. So what we have, the ratings, data set is in this format. Like the first thing is user ID, the second thing is product ID. In this case, the product is movies, and the third is the actual rating itself, like how much did the user rate this particular movie on the scale of 5. The fourth is the timestamp. So that's how the data set looks. I think I can check like how big is this data set. I can do a ratings.count, and I have somewhere around like I think 1 million records, 1 million ratings for this data set. So we can actually, so what we are going to do is we'll actually split this data set into training and test data, something which is like 80-20, and train a model with some 80% data, and then we can just do some predictions against 20% data. The goal is not to show the ML part itself. I'm not an ML guy, but just to show like how easy it is to use the ML API with Spark. So we have ratings. So for this purpose, what we are going to do is we are going to do some prediction. Like we are going to take 80% of the data, and we are going to learn a model, a recommendation system model, which is based on an algorithm called ALS, which is alternating least squares. This is an MLlib program itself, so you can actually use this program if you have the data set in a certain format it requires. So this requires your data set to be in certain format. Like for example, the training data set need to be in a format where you have user, product, and rating. So you need to create something called as a rating object, which is of this format, and give this to the ALS algorithm to train it. So we can quickly do those things. So for example, I have ratings, and I wanted to transform this rating into the rating object that the ALS requires. So in this case, I have to, when we are reading from the S3, each line is actually a string. So you can see that when we created RDDs from these users, you can see that it's actually RDD of type string. So each line is represented as a string right now. So what I have to do is I'm just splitting it first with this delimiter, like I'm just separating it into columns. And I'm going to create a ratings object, which is part of the Spark MLlib itself. So I'll get here is a rating object definition. So I'll import this class, and I'm going to construct this rating object, which is, I can have the result of this as y. I can construct a rating object which is of 3 columns. I don't need the timestamp column. So I can just say y1 and y2. Right. So what I did is I took the input records, which are strings, and just transformed into a set of rating objects. So let me just run it. Okay, so okay, it needs int. So we are splitting and it's still string, so I'll just convert to integers. So now we have a map partitions RDD, which is like the ratings RDD itself. So I can name this as ratings RDD. Okay, so we have a ratings RDD which is required in a format which is required by the ALS algorithm itself. So what I can do is since the ALS is an iterative algorithm, since it's going to consume the data set multiple times, I don't want it to hit S3 every time. So I'm going to cache this data set upfront. So I'm saying cache this data set. And and I'm going to use this cache data set after this. So ratings RDD will be cached once we run it. So I'm going to run this ML algorithm right now, which is ALS. I think ALS has some parameters like rank, lambda. There are some set of parameters for this algorithm. I'll just specify some parameters. Okay, so I haven't split the data. So I want to split the data into training and test. So let me do that first. So I'm taking this ratings RDD and I can split this ratings RDD using a random split function into 80-20, and I'm creating training and test right now. I'm caching both these datasets. So I'm partitioning the data into training dataset and test dataset. So okay, so now I have two different datasets. So yeah.
So would your ratings RDD still be cached at this point?
No, it is a lazy operation.
Okay.
I think if I run a count or any type of action, it will trigger a caching.
Okay.
So any type of action. So there are multiple actions. I think if you run the ML algorithm itself, that in itself is an action. So that will trigger the caching for the first time. After that, it will reuse the cache.
Okay.
So question.
Yeah.
You want training cache to be cached?
Which one?
Even after splits of 0 dot cache.
Oh yeah, it need not be. I mean, I need not have cached this thing. I could have actually split the data and cached this. Split data. So I need not have cached the original data set.
So by default, nothing is cached.
No, by default nothing is
It goes
cached.
to
Yeah, by default, yeah. It's a very common, like there was a common misconception that Spark uses everything in memory, which is not true. It doesn't cache by default anything actually. Some algorithms, I think if you use some MLlib or graphics, internally it triggers caching for you because it is better if it caches it. Otherwise, by default, it doesn't cache at all. Everything is on disk.
So otherwise, it will go back in parent relationship back.
Yes, otherwise I think unless the training algorithm itself was triggering a cache, which I'm not sure about it, if not, it would have read from S3 every time.
Every time.
Yes. It would have read from S3, it would have constructed rating objects, and then it would have done the processing for it every time. So that is the example. So I'm gonna, okay, I missed the train thing again. Okay, so here is als.train. So I can specify als.train. ALS, I have already imported the ALS algorithm implementation somewhere here, yeah, over here. And so I'm saying als.train and give this training dataset as an input. I think it also takes in some additional parameters like rank, number of iterations that you want to run, and lambda, which I don't know what it is about. So here I'm training, it's actually running the training itself. And the result of which is like you will get the model back. So I could have actually initialized a model variable so that will capture a model back. I didn't do that, I'll just rerun the training again. So you can see that I got a matrix factorization model, and I could have done this where I train this dataset and get the model back and store this in a model variable. Now I can actually do predictions against my test dataset. So model has an API called predict where you can pass the test datasets and it will do the predictions for you. So we can do that also. I'm not going to go more than this. So we can actually predict and where we can send the test data itself. I think it needs to be in the format where I think the test data, for example, right now we have ratings RDD having the actual rating also. I think the prediction requires only the tuple, which is like, I think it requires only the user and the product tuple. So let me just transform it that way and just launch the prediction step for you. For instance, so yes, so they just want a tuple which is like user and product. They don't need the rating. You can use the rating later on to compare the results. So I can say something like X, and it needs a tuple which is x.user, x.product. Like we are already, so X is a ratings object here, because if you look at test is actually created from splits, which is created from ratings RDD. Ratings RDD is already converted the existing record into ratings object. So here what we are operating on, each record is actually a rating object itself. We are just extracting user and product, not the rating, just creating a tuple of 2 and passing it to a predict function. So it will do the prediction back. I think I need to invoke a action to get the results back. So it will do the prediction back and actually get the results back in the RDD itself. For example, we have seen like we pass the test data, which is like 4904 is some user ID and there is some product ID, and it has done the predictions where this user for this product, for this movie would have predicted this 4.9 rating. We have our original ratings in the test data that we could have actually go and compare the ratings and do a root mean square analysis on this thing. So I think all those, those examples are very well provided here in this compute RMSE function, where you can send your test data and your model, and you can do the prediction about like how much is your error rate of your model right now. And this example, like it's a little more involved, I think. So what you can do is you can, for example, you can also do some things like, in this case, we define these parameters like model parameters like number of iterations. So you can actually iterate against, the model training itself took very little time because it's a very small dataset. So you can iterate against a set of parameters and you can actually choose the right model based on whatever is the least square error. So that's a quick overview of how you can use. So similar to these MLA algorithms, all the graphics algorithms are also very similar. So they have these nice higher level APIs to perform these computations. I think I can take some questions if there is any, and then we can talk about that. Yeah. Yes.
On the caching.
Yes.
Is it possible to name the cache so that
the name of the cache is the variable itself. Ratings are _RDD is the cache name.
so
We cannot explicitly name it as I understand. The variable name is the cache name.
so if I run the program again,
Yeah.
if I write it as a program, and run it again, so it's going to load everything from S3 and
I think yeah, if you shut down so the cache is available as long as the executors are running. In the Spark application is running, and there are executors that like the worker processes are running which have cache data.
no, that works in the notebook environment.
Yes. If you pull it down, you have to redo it. Yes. Yeah. So I mentioned the other environment, like there was an analyze environment I showed you initially where you can dump the Scala snippet. That launches the application, does the computation, and actually shuts it down like when it does the computation itself. So in that case, you will actually redo the whole stuff. So it depends. So how you need it? So what is the use case? Like if you have a use case where you want to cache and make the cache available, that's why I had a point about job server. That's why we have that kind of API where you can have a app running for some time. You can cache something about the ratings RDD and tell the users, okay, this is the application where there is ratings RDD. They can actually write any kind of Scala code against the ratings RDD and submit to this application. So that's where the job server comes in.
So map and Git are available as native operations within Scala, right? For Scala connections. So what makes it a Spark job here? Is it just the RDD or?
So what Spark did is basically took all these higher level operators and made it available in the RDD abstraction itself. Okay. It is actually doing it in a distributed fashion. So I'm playing with a small dataset here. You could have actually loaded a 100 GB dataset and also done it with, like, for example, you could have had a 100 node machine, 100 node cluster, and you could have loaded a 100 GB dataset and you could have done it in parallel. So Spark is breaking things into partitions and running these processing in parallel for you.
So RDD is like a special type of collection where the operations are to run the Spark job and
RDD is like an abstraction. It says like, so RDD is actually an interface. It says like, where is my dataset, how the dataset is partitioned, and what computation I need to run on each of the partition. For example, when you say map operation, here I'm expressing some function, right? I want to convert the string into split into columns and convert it into a rating object. This is actually a function. So the RDD will actually have the definition of this function. It says like, my previous RDD is this guy. It has 3 partitions, and each of these 3 partitions you need to apply these functions and generate this new RDD. So it's like an abstraction.
If I don't shut down the Spark instance, then that variable name is within the instance or?
Yes, the variable names are within the context of this application. So if
somebody else is running different notebook, it is the same.
No. So each notebook has. Okay, so that's a good question. So each notebook by default in our environment right now shares the underlying application. the Spark application. If you want, you can actually create multiple applications. So there is something called interpreters. So this is the underlying application configuration where I have just specified like we need 2 instances of 2 GB, okay, 2 GB driver memory and 4 GB, not 5120, 5 GB executor memory, right? You can actually go and create one more interpreter, say like, this is my test interpreter and I want this Spark, and you can actually override your configuration if you want, like depending on what you want. So now I have a new application called TST, and going back to this notebook, there is something called as a settings icon which says like which application I want to submit to. So when you create a new notebook, you can bind to a different application which other people are not using. So by default, the notebooks are sharing the application, but if you want, you can have your own application also.
So the variable names are shared across?
Yes, by default, yes. By default, yes, it is running against, it is right now optimized for these type of single user use cases. We are actually working on something like where if you have parallel users, you will have, by default, it will have a separate application. It is not exposed to API right now, but it is already available. It's a difference in how we default it, whether it's shared or not. That's the question. Okay. So you could have actually just, you could say like just go to TST and just submit to it and just submit the application there. You could have done that. So. Okay, so any other questions? Okay.
Are you supposed to shut down the cluster separately through the control panel?
Okay, so yes, good question. I think one is this Spark application itself. This is a long running application. To shut it down, you can do something like sc.stop, which will actually stop this application. Like this is the application stop. It doesn't shut down the cluster. To shut down the cluster, you need to go to the control panel and just hit this red icon here, and it will go and shut down the cluster. So if you actually stop your own application, that's good enough. Like I think once I share it, you will be sharing the clusters. So don't shut down the cluster because other people might be using it. What you can do is you can just stop your own notebook application, and if everybody has stopped, if the cluster is idle, we'll go and bring it on automatically. Those are already done. So those will be taken care of. Anything else? Okay, so I think I had few slides more, but I'll just share the information first. So this is the username which okay. First you can log into api.qbold.com. This is the URL, and you can hit qbold.workshop@gmail.com. So you can use this to sign in. Before you launch, just wait for some time. I'll just create clusters for you guys, like multiple clusters, so that you don't conflict with each other. You can log in. So the thing is, like, once you log in, you will see on the left, you will see a bunch of things. Like control panel is the first thing you have to look at. You won't have the ability to create clusters. I'll create the clusters for you, and you can. So once you go to control panel, you will get the notebook link. So you can click the notebook link. You create your own notebook for yourself. Don't reuse the notebook of somebody else. You must be able to, if you go to the Spark demo cluster, you must be able to see my notebook, so you can see some of the things that I've did. Like here is the Spark notebook link where I have my notebook. My notebook name is Workshop right now. So you can look at the Workshop notebook, and you can try it out on your own notebook. Like the way you create a new notebook is here. Like you just create your own notebook here, and you can just try it out. I think, okay, you took it down? Yeah, question.
Can we access data, personal data that we have on S3 and play around with it, or does that require setting up our own account?
So currently I have set up this account with my credentials, which can access only my S3 bucket. So what I encourage is we also have a trial account. Like if you sign up, if you don't want to do this, like use my stuff, you can just sign up for it using your trial account and just provide your own access secret keys. I think you have a free account for 15 days. You can try it out. So you can try it out. So if you're already in Amazon, have S3 keys, just use that thing. I think that's the best way. So those are also available in control panel. If you just go through it, you'll figure out like where to configure these keys and so on. Like there's a place where you specify the storage credentials, like how to access S3, so you can configure your keys.
Once I close the notebook, I have to reload all the data again or no?
Once you close the notebook, it won't shut down the application. But we actually copy all these notebooks to S3, so even if you shut down and restart the cluster, you will get the notebook back, but you have to run the notebook again. Like, so there is this icon in the top which will just basically run all the paragraphs. So if you have shut down and restart, you can just run everything. So I think I encourage, like, if you have your own Amazon account, you're already using AWS, you must just sign up for a trial account instead, so that you have your own working space and just try it out there. All right. I have a few more slides, but I don't know. Good, thank you. All right, so I think I'll hang around here for some time, maybe in this room or outside, so we can just talk if you have some questions, or I can go through the rest of the slides. Okay, thank you. Thanks a lot.